All right, today's administrative notes, before I get started talking about motion diagrams, I want to talk about lab number 2 while you're working on it. First off, yesterday I went to medical. I was gone pretty much most of the afternoon. I need to make the time up, both for the school's purposes and to be available to you. So I'll be here Sunday evening after 18:30, after 6:30. So I'll be here Sunday evening, which is a good thing because we've got homework and lab homework due on Monday morning, okay? Now, I strongly suggest don't wait until the last night to do all this stuff. That's a lot of work to do in one sitting, okay? Be working on this, but if you're having technical issues, come see me this afternoon after 2 o'clock, or come see me on Sunday evening, okay? I will not be granting extensions due to technical difficulties. Otherwise, everybody's system is going to end up breaking the night before. So you see where I'm going with that, okay? Now, next thing, I do want to talk about the grading I've done so far in lab number 1. I have not finished the grading. So how do you know when it's been graded? Well, first of all, I'm doing things in alphabetical order. But what you do is when you bring up the assignment, all the ones that are manually graded will have a graded by so-and-so, and it'll have that number there, okay? So that's the first thing. Let me address about the answers, though. Well, let me back up, back to the technical. So you want to make sure that your files are uploaded. And the way to test to make sure your files are uploaded is after you've uploaded the file, if you've got a yellow border around your answer, around your question, that means that the file has been saved but has not been submitted. That means I can't grade it until it gets submitted. Push the submit button in that question. Then the border will go away. You'll get the green check. Fingers crossed the green check shows up. But more importantly, you will also get a hyperlink of where you upload the file. Next to the button where it says upload the file, you'll get a hyperlink with your file name there. If you click on it, it will download that file from the WebAssign server, and what you see there is what I'm going to see when I grade it. So that's a way to check to make sure that your files have been uploaded. Okay? All right. Let me address the short answers. I talked to one section yesterday, so if you've heard before. I've got 65 of these things to grade, which means I really appreciate it if you can answer the question and then move on. Okay? Let me put it this way. I know y'all in high school English, because I certainly got it when I was in high school as well. Whenever you have a question, you restate the question in your answer in a form of a statement and then answer the question. You don't need to do that, because when I grade it, I will have the question right in front of me anyway. Okay? So just give me the answer. Another habit that shows up, and this is not necessarily from English class, but because of this step and this thing and this thing and this thing and this thing and this thing, here's the answer. You see what I mean? And I can understand that. I certainly write that way sometimes too. But you need to get yourself in the habit of doing answer the question first, then put in the justifications if asked for. You see where I'm going here? Answer the question. Just tell me what the answer is. If I have time, I can go into the justifications. Real world scenario. Way back when, I worked on a 2-star admiral staff. Okay? We had a standing procedure because our job was supposed to do the research to get the information to the boss so the boss could make the decisions. Okay? So we had to take whatever the question was, whatever all the research was, all of that, and condense it down into a 1-page executive summary. Here's the question, here's the answer. Boom. First paragraph. Here's the answer to the question, is in the first paragraph. The next paragraph gave some high points of this issue, this issue, this issue, this issue needs to be dealt with, etc., etc. And then contact information. If you have any questions, please call me in and that sort of thing. Okay? One-page executive summary so that the boss can take a look and see this is the recommendation from the staff, or here's the pertinent information I need to find. Okay? The other side of the folder had the 100, 200, 300 pages of raw information with tabs on it so that when the boss does have time, they can go look up the information themselves, cross-check. Plus, it also keeps you honest as well. See where I'm going here? So let me summarize it back up. And this is true in your other classes as well. When you're asked a question, first answer the question, then justify it. After all, in your English class and your essays and stuff, isn't your first paragraph usually something to the effect of, this is what I'm going to tell you about? See what I mean? Now, creative writing, that's a different animal, because creative writing, you want to build a sense of suspense, but that first paragraph, you still got to set the scene, right? Okay. All right, so enough of that. Let us now move on and let's talk about this concept called motion diagrams. What are motion diagrams? Simply put, they're diagrams of motion. What do I mean by that? Well, let's take a look at a car, for example, or a bird, or a horse, or a cart, or whatever the case may be. If we have a car rolling down the road, if we have a cart rolling down the road being pulled by a horse, if the body is rigid, and I use the word rigid pretty fluidly, because obviously when a horse is walking, its parts are moving all over the place, but what about the shoulders? What about the hips? What about the belly? You see where I'm going here? Everything is moving at the same rate. If you look, the best example is a car. If you look at a car, the front bumper has the same motion as the back bumper, which has the same motion as the mirrors, which has the same motion as the door handles. You see where I'm going here? So do I need to draw a picture of a car each time I want to look at its motion? The answer is no. In fact, when they're doing videos of cars in accidents, they put those stickers up. They're not tracking the car, they're tracking the sticker. You following along? So we don't need to draw a car. All we got to do is mark a single point on that car and track that point. So far, so good, right? Then I don't need to draw pictures. What I do is I can take successive snapshots of the car in its motion, successive snapshots of that point, and use those marks to calculate the motion of the object. So if a horse is running, you look at the shoulders. Where is the shoulder moving? Okay, you look at the cart, you look at the reins, or you look at the axle. Okay? Baseball player, football player, basketball player, you look at the hips. Well, you're supposed to look at the hips anyway, because where the hips go, that's where the body's going to go, right? Okay, but the reality is we just keep track of that one point, and we can do our analysis of the motion. For example, here we have a car moving from the left to the right. Let's make life a little bit easier, and let's say that the right is positive. Okay, left side is negative, right side is positive, so the car is moving from the left to the right. Describe its motion. Okay, yes? Okay, don't couch the terms, don't try to walk the fence, just give me a description. Okay? Take a look. What kind of motion do we have here? It's a constant velocity motion. What direction? In the positive direction. Okay, now how do we know this? Well, here's where the motion diagrams come into play. Here's how we're going to do it. And by the way, we've done this in lab number 1 and lab number 2 with the vectors. First thing we're going to do is we're going to look at this in a scale. Best way to do it is to take a ruler or something and say, for example, on a map, you would say 1 inch is equal to 10 miles. So if you draw a line that's 5 inches long, you've got yourself a 50-mile long space. Make sense? Okay, well, we can measure the distance between each one of those points. And that could represent, for example, a meter. 1 centimeter represents 1 meter, for example. That would be one way of doing it. The old Mythbusters television show, you saw how they would do that? They would have a cross-hatched background alternating colors. Each one had the same length. Foot, 6 foot, 3 foot, meter, whatever the case may be, black and white. So you can mark the position of the object as it moved. In this case, what we're going to do is we're going to draw an arrow between each of these points. That arrow is going to represent the displacement vector. So for this first point over on the left-hand side, where are we going to start? And where are we going to stop? Where do we start and where do we stop? Yes? Oh, okay, how far? Okay, since we're talking about a displacement vector, the displacement is the change in position. So here's the starting position, here's the ending position. That's a displacement vector right there. Easy, right? We just do that for every one of those. And now we have a series of displacement vectors. Okay, wow. Hard, isn't it? Each one of those displacement vectors happens to be 1 meter according to this particular scale. Now the next step is, how do we turn those displacement vectors into velocities? Well, how do we calculate velocity again? No, not distance over time. Displacement over time, because velocity is direction as well. That means we've got to take each of those arrows and divide it by a time interval. Fortunately for us, we do know the time interval. The time interval is going to be whatever the time interval is between each of those pictures. Does that make sense? So let's say, for example, there's half a second in each of those time intervals. Then that means that at time 0, we're at the first position. At time 0.5 seconds, we're at the next position. At time 1 second, we're at the next position, and so on up the line. We now know the distance. We now know the time interval. What is the velocity for each of these arrows then? 2 meters per second. Exactly right. Each interval has a velocity of 2 meters per second, and now my arrows can represent the velocity vector. You see where we're going here? So the velocity vector and the displacement vectors are going to look the same. The difference is the displacement vector is the actual distance or the actual displacement on the graph, on the mark, and the velocity vector is the displacement vector divided by the time interval between each frame. So far, so good? Okay, excellent, fantastic. Now we're going to have a little bit more fun with this, because now that you know how to do that, you should be able to give me the acceleration. So here's my exercise for you. I want you to take these whiteboards, make motion diagrams to show the acceleration arrows for this particular exercise, okay? The car is starting in the negative direction and is moving, starting here in the negative position, moving into the positive direction, and the space and the time interval is equal for each one of those. You will not be calculating an actual time or an actual number. You're going to be calculating relative lengths of your arrows, okay? To make the acceleration, and to find the acceleration or to make the acceleration arrows is not hard. Remember our definition that acceleration is the change in velocity divided by the time interval. Just like velocity is our change in position divided by the time interval. So if we take the change in position divided by time, we get velocity. So if we could find the change in velocity and divide it by the time, then we would get the acceleration. So how do I find the change in velocity? Well, first of all, I got to make the velocity arrows. Fortunately, the velocity arrows are just going to be the same thing as the displacement arrows. So there's the velocity arrows, okay? The next step is I've got to find the change in the velocity. We did this in lab 2, right? I kept beating on that, and initially it was like, how do we do that? But then by the end of it, we kind of got it down, right? Which is stack the arrows. Make the arrows start at the same vertical line and stack them up. So we have position 1, time 1 on the top, time 2 at the next, time 3 next, time 4 next. Then, to find the change in the velocity, all we need to do is to draw an arrow from the head of V1 to the head of V2, or from the head of V2 to the head of V3. In other words, the way I have it written out there, from vector Vi to vector Vi plus 1. So far, so good? Now, just to make it stand out, just to make it pop, I use different colors. And so therefore, there's my delta V's. The red arrows are my change in velocity. Okay, now again, just like we can take the displacement arrows, divide those by the time interval and get the velocity arrows, we can take the change in velocity arrows, divide them by time, and get the acceleration arrows. And so the red arrows will now represent our acceleration. What kind of acceleration do we have here? Positive, constant. Okay, so we see that the velocity is increasing at a constant rate. Okay, now a couple of you, when you did this, your delta V arrows got longer and longer and longer. And I can understand the mistake. You have to pay attention. This is where a ruler would really come into play, because you would have to mark out each of those stacked arrows at the same length as the ones that you have in the diagram itself. So instead of, for example, you're supposed to go 1 meter per second to 2 meters per second to 3 meters per second to 4 meters per second. That means you're adding the same length on each one. Some of you, what you ended up was doubling the lengths of your velocity arrows. That would be interpreted as 1 meter per second to 2 meters per second to 4 meters per second to 8 meters per second. And so your arrows get significantly longer. And that's why you may have seen some errors in your acceleration arrows. So rulers really come in handy in this case. Okay, now here's an interesting thing. What can you tell me about the sign of the acceleration? It's positive. What can you tell me about the sign of the velocity? It's positive. Okay, so let's try a different exercise. This time I'm going to take the vehicle and have it slow down. Still going from left to right. But this time, well, I shouldn't be telling you it's slowing down. You should be able to figure that out on yourself. Make the velocity and the acceleration arrows for this exercise. Okay, so looking around, you all got the right idea. Yay, you all got the right idea. Step number 1 is we want to draw the velocity vectors. So there's the velocity vectors. Then we want to stack the velocity vectors. And then from that point, we draw the change in velocity vectors, which means from the head of time 1 to the head of time 2, and so on down the line. So there's our acceleration arrows. Because if we take that length and divide it by the time interval, we can calculate our acceleration. And so on the graph right there, we would see the velocity is pointing in the positive direction. What direction is the acceleration? In the negative direction. So we can start answering some questions here. If both the velocity and the acceleration are positive, what is going to happen to the speed? It's going to increase. Excellent. If the velocity is positive and the acceleration is negative, what happens to the speed? What does it do? Decrease, just like that last one. If the velocity is negative and the acceleration is positive, what happens to the speed? It decreases. It decreases. Let me go back to that diagram right there. This diagram, we're assuming that the left-hand side is negative and the right-hand side is positive, yes? What if I flip the signs around? So that the left-hand side is positive and the right-hand side is negative. Then we have a negative velocity with a positive acceleration. What's happening to the speed of the object? It's decreasing. It's decreasing. I'm trying to unlearn that. Positive acceleration does not mean speeding up. Okay? Positive acceleration is the direction of the change of the velocity. Which leads to the last question. If the velocity and the acceleration are both negative, what happens to the speed? It increases. That makes sense? Okay? Draw your arrows and you'll see what I'm talking about. Okay, so what that means is negative acceleration does not mean that it's slowing down. It could be slowing down. if what? If the sign of the velocity is what? Positive. If the sign of the velocity is negative and the acceleration is negative, it is. We should have worked out that rule in lab number 2. The sign of the, if the signs are alike, what happens to the speed? If the signs are different, what happens to the speed? What an easy rule, isn't it? Yes. Okay, you're going to see that in lab number 2 homework. Question? We're not talking about multiplications here, so I don't want to quite phrase it that way. What I want to do is instead, I want to look at the arrows. So for example, in this case, because the arrows are in opposite directions, you see what's happening to the lengths of the velocity arrow? But in this case, because the arrows are in the same direction, what happens to the length of the velocity arrow? Do you see what I mean now? So it's not a multiplication, it's the lengths of the arrows. What happens to the lengths of the arrows? Do they become more positive, more negative, and so on down the line? All right, I got one last exercise for you. Cars moving from left to right. Again, let's let positive be to the right. This time I want you to draw a position versus time graph, a velocity versus time graph, and an acceleration versus time graph for the motion. Okay. I was walking around, and most of you have got a pretty good idea of how to do this. But I'm going to show you a couple little tricks along the way to make things a little bit more interesting. First of all, the displacement vector, or the position graph, is going to be easy. Here's your position vectors. Here's your displacement vectors. So all I need to do is stack them one on top of the other. So for example, I start off with the first one with an arrow that likes that, and then I take this one and I add it to the next arrow. And then this one adds to that, and so on up the line. Because after all, that's what position is just adding all of those arrows together, do you see? As time progresses. And so you end up getting a position graph that looks like that. Okay, cool. What about the velocity and the acceleration graphs? I'm going to show you a trick that's going to blow your minds. Okay. All right, let's start off. First, do we agree that those are the velocity and the acceleration arrows? Okay, now, here's what we're going to do. Let me bring up my whiteboard here. Let's start off with the velocity arrows. So I'm going to draw, let me do it in blue. So that's the first velocity arrow, then the next velocity arrow, then the next velocity arrow. So your velocity arrows should stack to look like that, correct? Okay, now here's the cool part. We know that the velocities are changing as time goes forward. So this direction right here is the time direction, isn't it? This direction right here would be the magnitude of the velocity, yes? So why don't I just turn it on its side and draw that thing? Or I will say this. Another way we could do that is we could go ahead and draw the axes of the velocity versus time arrows, time graph, and just draw the arrows vertically like that. Because after all, that's the positive velocities. You see where we're going here? Okay. Now, what about the acceleration? Well, the acceleration arrows look like this. Oh, I'm sorry, I got that wrong. Hold on. Thank goodness for Control-Z. The acceleration arrows look like this, going in this direction. All right? Now again, we could go ahead and stack them, and if we stack them, we would get the arrows looking like that. And so what we would end up getting is something that looks like that. Okay? You following along, guys? That's really a neat little trick to take those arrows and rotate them, yes? Okay, and so we end up getting the velocity arrow. We end up getting the velocity arrow. The velocity diagram looks like that. And the acceleration diagram looks like that. So, all good? So, and by the way, it kind of makes sense because if we look on the velocity graph, don't we see we have a constant slope on the first part, which means we have a positive acceleration. Then we have a zero slope, which means we have a zero acceleration. Then we have a constant negative slope, which means we have a negative acceleration. So that ties the slopes with the graphs. We have a question. For a decrease in velocity, what it would look like was you would have it would slow down. So in the first part, we see the object is speeding up. Then in the next time interval, we see the object maintaining its speed. And then the next object, because the velocity is positive but the acceleration is negative, we see the object slowing down. See where we're going here, guys? Does that make sense? Well, because okay, why? The question is, why do we have this straight drop on the acceleration instead of a slant on the acceleration? We can do that, but let's take a look at the velocity graph. The main reason why is this, because on the velocity graph, at the very top, when we get to, there we go. When we get to this point right here, then we have to transition from the positive velocity to a zero velocity. Now, because I don't have a lot of data in between, we're only taking it every 10th of a second or every second or whatever the case may be. If I was taking the data every 100th of a second, then I may end up getting the curve. Do you see where we're going here? This is a case of the precision of the measurements, or the precision of the time intervals. Okay? But in essence, we can still describe the motion, which is speeding up as it's moving away, moves at a constant speed, and then slows down as it moves away. Okay? Any questions? Any answers? Okay. Well, that's going to finish up today's